And we are back for the second hour here, part 4 of chapter 18, Wednesday, July 1st. Remember, Friday, July 3rd, no class, so enjoy your extra time there. But don't get too complacent because Monday, July 6th, we have test 1 due, upload to Learning Suite by that midnight. But also on Monday, July 6th, we'll be going on to chapter 19. So no rest for the weary. Sorry about that. That's how fast this class moves. So we'll have two more class periods on this day also to help you with the next section. But 19, of course, is not on test 1. Test 1 is just 16, 17, and 18. Okay, what we're wrapping up today. And because we're finishing chapter 18, of course, homework 3 is due tonight. Sample test 1, we'll have time, I think, in this hour to go through some of those problems. Click through at least the answer part of that. But look through and work those sample test problems. You have 2 files there. You have the blank test there that doesn't show the answers, and then you have the key. And on that key file, it also has the solutions to the worksheets that are a collection of harder problems. Now, don't go and start looking at those worksheet problems or the harder problems on the sample test before you finish all 3 chapters and doing enough homework. Don't psych yourself out. I only put a couple harder problems on a test. So these worksheet problems are harder problems that have been on older tests. Sometimes I do put them on the tests we're going to cover, so it's to your advantage to look through them and do that. Also, we have quiz 3, which is due on Thursday tomorrow, and that's on chapter 18 here. Okay, so it's a couple naming. There's an NAS problem. In fact, that one we just helped you out with on the board there. And then there's a couple synthesis problems. And that's what we're going to do now, this hour. We're going to do some synthesis problems. And I like to point out the economics of this. Okay, these are all products, commodity chemicals that are sold on the open market. And a lot of different companies make analogs of different drugs as part of their MedChem program, or they have different products for different applications, whatever they may be, fuels or additives or cleaning agents, whatever, all sorts of applications of these aromatic compounds. And here's the prices of a couple of them here. So here's what, para-ethyl versus meta-ethyl. And look at the price difference. 53 bucks for 100 mils or a couple ounces of that. Pretty expensive. Not too bad though. But look, to buy a couple ounces of this 100 mils of the meta one, it's $400. Why is it almost 10 times more? There's probably a problem with how it's made, right? It's more costly to make the meta one as opposed to the para one. How are we going to make the para one, by the way? Let's see. We can take ethyl benzene. So that's one step, company has to invest some money in that. Maybe buy that from another company and then do the couple of steps. And then what do we need to do? We need to nitrate. So that's nitric acid, sulfuric acid, right? And that will give us the para nitro product. And then there's another step. Yeah, and this is a cheap one, right? This is one that requires, well, one step to make the ethyl benzene. And then 2 more. What's this next step here? Reducing a nitro to an aniline. What is it? The cheap one is tin, metal, and HCl. Okay, and that will give us the para product. That's the cheap one. Why is the meta one more expensive? Well, we need to start with this instead, right? And why? We need to do Friedel-Crafts acylation, right? Or there's companies that make acetophenone. That's that product there. But what do we need to do here now? Oh, we need to nitrate. That same conditions there. That will put on the meta nitro group now, because the aromatic ketone's a meta director. And then HCl, tin. Yeah. Oh, I'll just say same thing there. Okay. And those conditions are not strong enough to reduce the nitro, actually. It'll just reduce the aromatic ketone. And look, we got to do a 4th step then, We got to reduce that. We got to do Wolff-Kishner, the Clemenson. So let's see, which one can we do? Well, let's do the Wolff-Kishner here, hydrazine, and base, and that will give us our meta product. So you see, it's a one extra step, and that one extra step means something money-wise. But yeah, let's do some other multi-step applications now. Let's see, how about, which one do we want to do? Oh, we're going to skip benzene. We don't have enough time to do benzene. I know you're heartbroken over that, but don't worry about that section. You can read it. I may revisit it when we start to review for the final. It's just a simple thing. You can form benzene with strong base in the leaving group, and then you can add strong nucleophiles and get anilines or phenols. Or on the benzene, you can use that as a Diels-Alder or dienophile and react it with a diene and make a benzo cyclohexene. But yeah, we're not going to do that. I know you're disappointed. How about, let's do some other multi-step syntheses. And I think these are good problems because we give you the product and we ask you the steps to make it. Dibromotoluene, and it is the 2,6-1 from benzene. How are you going to make that? Let me draw a couple of these other ones up here. Let's start with anisole on this other one. And anisole, remember, is the methoxybenzene. And how are we going to get to this? Straight chain propyl chloroanisole. Okay. And maybe I can get one more up there. And let's start with toluene here. Now, I'll give you time to pause your video and work on these if you'd like to. I strongly recommend it. I hope you're taking careful notes as we go through these videos and following along with me. You got to physically engage with the material to help it reinforce in your mind. The more problems you work, the better prepared, of course, you are for the test. So you want to pause now, work on those three. And we're back. Let's see what we need to do. So we have to put on a methyl group here. So hopefully you had Friedel-Crafts alkylation there. That'll give us the toluene. Now you say, well, let's just brominate this thing. Well, these are the two ortho positions to the methyl group, right? The directing group. But look, the para position sterically is more available. How can we get this one exclusively in high selectivity and yield? Yeah, we have to block this position here first with sulfonation. So H2SO4, that will give us the sulfonyl toluene, okay? Now what can we do? Now we can brominate, bromine, FeBr3, okay? And that will give us this product with high selectivity. So this is with excess bromine, okay? And, you know, this is a deactivating group. It's a meta-director. So they actually enforce each other there. And then remember I said you can, what? Reverse the sulfonation with strong acid. And all you need to do is HCl and water and heat this up. And that will put a proton back on there. And you lose SO3. You use sulfur trioxide. But that's okay. You can just wash that away from this product. And by blocking this para position, you can then get the bromines at those sites. A quiz or a test, if you just took this directly with bromine to that and showed that, it'd be a low yield. We'd know what you'd mean, but I like to show the sulfonic acid blocking effect and the reversibility. We'll see that again with Propofol here in a second. You'll see how that's an important thing there. Anyway, so those steps there to do that top one. And what about this one? We've got aniline. We need to put on what? This straight chain propyl group. So we can't do Friedel-Crafts alkylation. We have to do Friedel-Crafts acylation, right? So aluminum chloride and the acid chloride from propionic acid, Okay. You don't need to show how to make that. I showed you from thionyl chloride and propionic acid, but you can just use these reagents as the acid chlorides directly, right? And that will give you the aromatic ketone and methoxy, right? Oh, we got to put on this chloride. So we need to react with chlorine and iron chloride, and that will put on that. And notice this is a meta-director and this is an ortho-para-director. So those are enforcing. And you always look for that. Why do we put on this first? Okay, it's because if we chlorinated directly here, we'd get chlorine there and there. Okay, here we'd also get some ortho product here, but again we can separate and get selectively the para product there. Okay, but now these are enforcing for each other, so chlorination goes on here, and then what do we need to do? Yeah, we need to do Clemenson or Wolff-Kishner. Okay, to make that the straight chain alkyl. Okay, and this is a primary position, so we have to make that indirectly from the acylation followed by the reduction. Okay, questions on that one? All right, what about this one here? We've got a nitro group going on followed by bromine. There's a couple ways we can do this. Actually, the order doesn't matter too much. In fact, we've done this now a couple times, right? We've made the para and the ortho nitrotoluene. I'm not going to do that. But we also, in that reaction, we can get this. Okay. Or we could have put the bromo on first, and that would have gone on as a mixture, ortho and para. But now, if we got this one here, the stronger donor group is the alkyl group. So the second electrophile going on is nitration. Okay. But we could have put this one on first as a nitro, and then you see that's also a meta-director, and this is a para-director. And then we could have brominated to get that similar. So this one ends up being a little simpler, but you got to analyze it and go through each one of them there that can help you out. Okay, let's try a couple more here. How about this one? Oh, let's give you a head start, starting with ethylbenzene. Can you get to this product where we've got nitro and bromo and a vinyl group there? So it is a styrene molecule. If you want to pause there for a minute, and we are back. So what are you going to do here? First, let's see. An alkyl group, yeah, is a para director. So nitrating that will give us this. Okay. Now, this is again an example where you could have done the nitration and the bromination in different orders. It'd still be similar there. But I think this one's a little bit better because the ethyl group's a little bigger and you'll get more of the para product in that case. If you try to put on the bromo first, it actually is diminished. But again, these effects will give you a break on that. So sometimes the order doesn't matter. Okay, this would be another one, but I'm just pointing out what's actually used industrially here. But then the next thing is bromination. So ferric bromide gives us the orthobromo. And again, that's not the radical bromination. That's not bromine and light. This is bromine and the ferric bromide. So we're talking about electrophilic aromatic bromination. Do we get this? And then what do we need to do? Now we do what? How are we going to put the alkene on there from the ethyl? Okay. Yeah, we're going to have to do the bromine and light, or we could do NBS and light and peroxides. There's a couple ways to do that. And that's specific for this benzylic position here. So our intermediate is a dibromide. The one that's put on the benzene ring came from the conditions involving the iron bromide catalyst, right? This one here, why are we putting this bromide on here? Well, because then our second step is T-butoxide, strong, hindered, bulky base. Won't do SN2 here. Okay, so you need a bulkier base to always do what? E2 elimination there, and that's how that's made. So that's probably a pretty expensive reagent. It's quite a few steps to make something like that, but you can see how that's related there. All right, let's see, a couple more. Let's do this one. I like this one. You've probably heard about this drug. I've mentioned it a couple times. What's this called? We have a phenol here and two isopropyls. That's right, this is Propofol. Okay, and Propofol is an analgesic reagent. It's also a painkiller. It'll induce anesthesia, and induce loss of consciousness. It's used often for minor operations and actually serious operations where the patient needs to be sedated for a long time. It's very fast acting. As soon as this hits the bloodstream, you're out, okay? It's only used in the clinic. It has to be used carefully there because if the anesthesia is too heavy, the person can go into a deep coma and even pass away. And that's what happened to the famous performer singer, right? Michael Jackson, about 10 years ago. He was using this drug at home. He had a physician giving him this drug, but that one night when he did pass away, he was given too much of this stuff, Propofol. Pretty simple compound, right? Diisopropyl phenol, two isopropyls at the 2 and 6 positions. How are we going to get those on there? Can you make that compound? And we'll start from phenol. We haven't showed you how to make phenol yet. It's actually made from cumene, isopropyl benzene. Maybe later on I'll show you how to make that, but you have to react it with peroxide and light and then strong acid, and it'll actually cleave. There's a migration, and you get out acetone and the phenol. It's kind of a neat reaction, but no, we'll show you later on how to make phenol from diazo compounds in the amine chapter coming up. But right now, what do we need to do? Well, Friedel-Crafts alkylation, right? So we've got the chloride and aluminum chloride here. And yeah, you can do that, but with phenol, the major product is actually this. And that's not what we need. So what are we going to do first to phenol? We're going to sulfonate it and block the 4 position, right? So if we treat it first with H2SO4 and get this, then we have those 2 positions blocked. Now, we've got to do Friedel-Crafts alkylation, but we have a withdrawing group here, okay? And didn't we just say strong electron withdrawing groups, no Friedel-Crafts? Yes, okay. That is what the book says, okay. But we also have a strong donor here by resonance, right? The phenol is a strong donor. So actually how this is done is you take this and treat it with isopropyl alcohol and strong acid, HCl, both of these in excess, and heat it up. Now, wait a minute, this doesn't look like Friedel-Crafts alkylation, does it? Yes, it is, because if this protonates here, the true electrophile ends up being what? Isopropyl cation. And that's the secondary cation, it's okay. And then what? We get substitution at the 2 ortho positions. So we get the sulfonyl propofol, the diisopropyls, and that's for the heat and a long time. The yield's not great. But this is actually how it's made. Okay, so you can do Friedel-Crafts with a strong withdrawing group, but you have to have a strong donor also present. Okay, so good yield of that. And then this here is more strong acid in a separate step, water and heat will drive off the sulfur trioxide. And the mechanism, involves protonation at that spot and then loss of a proton there, and then you can kick off the sulfur. You can push the electrons and do that mechanism. We've shown you enough there for that, but to make the analgesic drug, it takes a few steps. So all the way from cumene, well, it's from phenol, it's what, 1, 2, 3 steps. Yeah, very, very inexpensive, very useful drug anyway, as long as it's used correctly. Now let's do the really tricky one. So if you're okay with that, Let's see. How about this one? Let's start again with cumene. So sometimes, especially these harder ones will give you a starting point there. And let's get to this product. Now, I have to warn you, this product is going to look very intimidating. And you're going to say, wait a minute, is Dr. Andrus just going to be trying to flunk us all here? No. But that's an intimidating looking product, isn't it? It's Hexa substituted benzene. So how are we going to take the cumene there, the isopropyl benzene, and get to this? Okay, we've got two amino groups on there. It's an aniline, you can say. It's got two chlorides of bromide and an isopropyl from the cumene. Now before you drop this class, throwing up your hands and getting mad at your computer or me, let's analyze this stepwise and see what we've got here. So yeah, we've got, two chlorides here coming in. Maybe we could put those in at the end after we have what? Two nitrogens on there. And the anilines, remember, are very good chlorinating agents. So a couple ways we could do this approach if you start to look at it. And two groups that are the same means we can bring them in both together, right? So it becomes a little simpler that way. And so working backwards here kind of begins to make some sense. So if we work backwards on this and think about that, could we put those two chlorides in at the end? And these type of problems, you just have to kind of experiment with things and try different things. And if you take a couple steps back, usually things will become clear, especially if it makes sense. Should that reaction work very well for this last step? Yeah, if we have excess chlorine, and we actually don't need the iron trichloride, just excess chlorine will do this reaction just fine on its own to form the dichloro part there. So now we're to this, and let's see. So what can we do there? Well, we only know one way to make these amines for the aniline part there. We know how to do the reduction of the nitros. So yeah, we can put on a couple nitros, okay? And let's see. So yeah, we know how to do that. HCl and tin. Okay, SN stands for stannane. That's the Latin name for tin. In case you were wondering why I was calling SN tin. Okay, there's a lot of these Latin names lurking in the periodic table. Stannane is the Latin word for tin, but we'll just call it